Section 3.6 deals with the leveling effect, and we've spent a lot of time talking about acid-base reactions, but we haven't talked about choosing appropriate solvents for acid-base reactions. So it says here that a good solvent should be able to surround the reactants and facilitate their collisions without itself reacting. So we want the solvent just to solubilize or dissolve our reagents, but we don't want it to undergo a reaction itself. So because water can act as an acid or a base, it has what's called a leveling effect on strong acids and strong bases. So acids stronger than hydronium cannot be used in water, and bases stronger than hydroxide cannot be used in water. And we're going to try to figure out why in the next couple slides. So more on the leveling effect. So this slide says an appropriate use for water as a solvent when a base is not stronger than hydroxide. So that was one of the bullet points that was covered on the last slide. So what's going on here is we have a polyatomic ion. We haven't covered this polyatomic ion yet, but this is called an acetate. It's called an acetate ion, and that's reacting with water, and we see we have some kind of equilibrium here that produces this molecule. This is called acetic acid, and of course hydroxide. And if we label our acid and base, so this water is behaving as the acid in this case, and then my acetate must be the base, and then over here I have my conjugate acid, good practice, and my conjugate base. Alright, so what it's asking us here is, would water be an appropriate solvent to dissolve acetate? Can I dissolve acetate in water, and will it be affected by the leveling effect? And if we take a look at the equilibrium here, so we look at the pKa of the acid, water, which is 15.7, and my conjugate acid, acetic acid, which is around 4.75, I can see that water is a much weaker acid than acetic acid, so my equilibrium is going to lie to the side of the weaker acid, so it's going to lie hard to this side. So that means that with water as a solvent, the acetate will react with water, but the equilibrium greatly favors the left side, so water is an appropriate solvent to dissolve acetate. There we go. Because, again, we could frame it as the acetate ion is a weaker base than hydroxide. More about the leveling effect. It says because water can act as an acid or a base, it has a leveling effect on strong acids and bases. And here we're going to look at an acid. So in other words, if you have an aqueous solution of a strong acid like sulfuric acid or hydrochloric acid, so these are strong acids, they can really just be viewed as an aqueous solution of hydronium. And the main difference between concentrated sulfuric acid and dilute sulfuric acid is just the concentration of hydronium. So again, if we just examine the pKa's of the acids here, so this is my acid. I'm not going to label everything, but this is an acid, and then the hydronium is my conjugate acid. If I just go by a quantitative analysis here, I can see that the pKa is -9 and the pKa of hydronium is -1.7. So this sulfuric acid is a much stronger acid, so my equilibrium is going to lie greatly to the side that has the hydronium on it like that. So again, essentially what happens when you put sulfuric acid in water is that what you really have is mostly just a solution of hydronium and the conjugate base of sulfuric acid. So it says here that bases stronger than hydroxide cannot be used in water. For example, we wouldn't be able to use, it says we wouldn't be able to perform the following acid-base reaction in water. So let's just say hypothetically, and I'll get out where's my green pen here? I'll get out the green pen, and I'll say hypothetically, in question mark, because obviously this isn't going to work. It already told us that this won't work. But why can I not take these two reagents, right, this alkyne and this base, why can I not take those and mix them together in water? Why won't that work? Well, the reason why is because what's going to happen is that my base, so this is my acid, right, and this is my base, what's going to happen is that the base is stronger than hydroxide, so it's actually going to react with the water. So I'll put my H2O. So what I'm going to end up doing is I'm going to produce this amine plus hydroxide. And if I evaluate the pKa's, so where's my blue pen? The pK of water is around 15.7, and the pK of an amine is around 38. High 30s. So that means the equilibrium is going to lie completely, almost virtually completely, to the side of these two products. So because of the leveling effect, the water reacted with this base, which is a very strong base, and it produced hydroxide. So I cannot do this reaction in water, and the reason why is because of the leveling effect. Because the base is stronger than hydroxide. So it's going to lie to the side of these two products here, the hydroxide and the amine. So let's take a look at section 3.7, which deals with solvating effects. So this section just basically is trying to give us a rationale for the difference in pKa between tert-butanol and ethanol. And you can see that ethanol is a stronger acid. So it's a stronger acid, what? It's about 100 times, well, it's 100 times stronger. 100 times stronger acid, because each pKa unit represents an order of magnitude of 10, so 10 times. So 10 times stronger acid. So we can't rationalize this based on the areo concept. So we can't rationalize it based on the atom, because the conjugate base has the negative charge on an oxygen for both of these molecules. I can't base it off of resonance or induction or the orbital. So there must be something in ethanol, the reason it's more acidic, there must be some effect that's stabilizing the conjugate base more than is stabilizing the conjugate base of tert-butanol. And it says down here that the ability of the solvent to stabilize conjugate bases comes into play for this example. So if I look at the next slide, it says here the solvent must form ion-dipole attractions to stabilize the negative charge. So if I draw in the negative charge on my tert-butoxide and my ethoxide, you can see just by looking at the electrostatic potential map, you can see that the negative charge on the tert-butoxide, so here's the negative side that's shaded in red, and then I have the positive side that's in blue. You can see that the red or the negative charge is much more sterically hindered by these three CH3 groups. These are called methyl groups. So it's much more sterically hindered, or crowded by those, so to speak. So it says if the tert-butoxide is sterically hindered, it won't be as well solvated as the ethoxide. This is why tert-butanol is not as acidic. So again, our pKa here is 16. This is a stronger acid. So let me try to frame it a different way. So again, there's something that's stabilizing the ethoxide more than is stabilizing the tert-butoxide. So I have my ion, and then I have the dipole for my solvent. So I'll just draw in the delta plus for the dipole of my solvent. And you can see that there's more delta pluses for the ethoxide that are able to stabilize it just by virtue of the fact that the negative charge is not as sterically hindered as when I have this big bulky group on the tert-butoxide. So there you go. This is an example where we don't use areo to rationalize the difference in acidity, but we can use solvating effects to explain the difference in pKa. Counterions. Counterions are also known as spectator ions. So if you studied, total ionic equations and net ionic equations in general chemistry, I'm sure you talked about spectator ions. And this is an example down here of a reaction that I showed in class a few lectures ago. So I have my base reacting with water, and I end up with an amine and hydroxide. And you might have asked yourself, I see these negative charges. What's balancing out these negative charges? Shouldn't there be a cation? And the answer is yes. Yes, there should be a cation. But we assume that they are always present. So the cations are always present, and because they are necessary to balance the overall charge of the solution. So if we put in the counterion, so I would have, for example, my sodium ion here and my sodium ion here, but just like in general chemistry, we leave those out. Okay, so we leave those out most of the time in organic chemistry. So this is kind of just an FYI slide, but the take-home message is down here at the bottom. So it says that counterions are often left out of an equation because they do not generally play a significant role in the reaction. So if they're not involved in the reaction, we just leave them out a lot of the times in organic chemistry. There are maybe one or two exceptions that we would look at in the entire Organic Chemistry 1 and Organic Chemistry 2 course. So very rarely do we have to include counterions, but it's just, keep in mind that they are there. So the last section of chapter 3 deals with Lewis acids and bases. So if you remember the Arrhenius definition of an acid and a base, we talked about that in class, and then we talked about the Bronsted-Lowry theory of an acid and a base, and that's largely what this chapter is about. So a Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. But the Lewis acid-base definition says that a Lewis acid accepts a pair of electrons, and a Lewis base donates a pair of electrons. And if you're ever having a hard time remembering that, I kind of just go with an acid accept, so A and A, and then you get the B and D. Maybe you can draw some kind of connection there. Anyhow, so a Lewis acid is an electron acceptor, and a Lewis base is an electron donor. So acids under the Bronsted-Lowry definition are also acids under the Lewis definition. So here's an example at the bottom. We could regard this as a Bronsted-Lowry acid-base reaction, but we can also view it as a Lewis acid-base reaction. So if I take a look here, obviously HCl, this must be my acid, right? So it's a proton donor, and the water is behaving as a proton acceptor, so this would be a Bronsted-Lowry base. But I can also think of this base as being a Lewis base because because it's donating this pair of electrons. So this is also a Lewis base, And what about HCl? Well, it's accepting this pair of electrons, right? So this is also it also can be regarded as a Lewis acid. So it even broadens the definition of acids and bases. And what's so great about this is that some acid-base reactions cannot be classified using the Bronsted-Lowry definition. So for example, it says here, explain how this reaction fits the Lewis definition, but not the Bronsted-Lowry definition. So if I take a look at this BF3, so boron trifluoride, here you can clearly see that this is accepting a pair of electrons from the water, so this must be my Lewis acid. Okay? And the water is donating a pair of electrons, so this is my Lewis base. Okay? But it says here it does not fit the Bronsted-Lowry definition. And why is that? Well, I can see that the acid, my Lewis acid, it's definitely not donating a proton. It's definitely not donating a proton. So you can see how we have to use the Lewis acid and Lewis base definition to define what's going on in this acid-base reaction. So let's see here. This is the last slide. So this is question 3.32. It says, in each case below, identify the Lewis acid and the Lewis base. So I think the first thing to do here in A is to start by drawing the curved arrows. So I can see that I have my aluminum trichloride, and I have this molecule here. So this ketone, that's called acetone. So if I draw the curved arrows, you can see that I made a sigma bond between the oxygen and the aluminum here. So I'm going to draw the curved arrow like this. So hopefully right away you can draw a connection here and say, well, the AlCl3, the aluminum trichloride, that's accepting electrons, so this must be the Lewis acid. And this acetone, or this ketone, is donating a pair of electrons, so this must be my Lewis base. All right, if I take a look at the second one, I could start by doing the exact same thing and draw in my curved arrows, so I can see that the ketone, which is acetone again, is accepting the proton from the hydronium. So let me fix that arrow. So I can see that again the ketone, which is acetone, is donating a pair of electrons, so this must be my Lewis base. And the hydronium is accepting the pair of electrons in that curved arrow, so this must be my Lewis acid. So this covers the rest of chapter 3. So that it concludes chapter 3, and I hope you find this video useful.